Welcome to Lesson 10, Derivatives of the trig functions. Trig functions, particularly the sine and cosine waves, are really, really useful functions in mathematical modeling. So it's important that we bring them into our trig practice so that we get good at working with their derivatives. So we're going to begin with the derivatives of sine and cosine. And actually, I guess we'll start with sine. So I have a graph of sine of x here. And what we're going to do is kind of try to sketch a graph of its derivative similar to what we did in lesson 7, where we were drawing graphs of derivatives based on the graph of the function. So we're going to use like slopes of tangent lines, and we're going to see if we can just get a rough sketch of what this might look like. So what I would suggest we start with would be those places that have horizontal tangent lines. So any place where sine has a horizontal tangent line, then its derivative, which we're going to graph down here on the xy grid, would be 0. So at negative 3 pi over 2, at negative pi over 2, at pi over 2, and 3 pi over 2. Okay. And then we're going to follow along using the observations we made in lesson 7. On this left side of negative 3 pi over 2, we see that the sine function is increasing. So over here, this would mean that the derivative is positive. And it starts out steep, but then gets less steep and gets closer to 0. So we have something like this. And you'll notice, well, actually, let's just go ahead and do this piece first. We'll replicate our efforts in just a second. So from negative 3 pi over 2 to pi over 2, this function is decreasing. So from negative 3 pi over 2 to pi over 2, we're going to expect the derivative to be down here. And again, let's pay attention to its steepness. Well, it starts out, as we know, at 0, and then it's getting more steep until at a certain point, it kind of starts to get less steep again. So it starts at 0, gets more and more negative for a little while, and then less and less negative until it gets closer to 0. And again, you can kind of sketch out little pieces of straight lines to see that pattern. So I'm going to go something like this. More negative, bottoms out at a certain point, and then gets back to 0. And you'll notice that this is repeated here. It's the same exact function. So from pi over 2 to 3 pi over 2, I have the same thing. So whatever I drew here, I'm going to draw the same thing there. And last but not least, we'll kind of look at this section between negative pi over 2 and pi over 2. So sine of x is increasing. That means we're going to expect the function to be in the positives, the derivative. And same sort of pattern. Starts at 0, immediately gets steeper, kind of hits a max steepness, and then gets less steeper back to 0. So something like this. Okay. And we could kind of start that on this end. It's clearly, we didn't have the whole picture there, but that's okay. It's the same idea. So take a look at that graph. It's not perfect. We're doing some estimation, but does it look familiar? I mean, I know I'm not necessarily saying that this is 1, 2, and 3 because I didn't try to estimate the values, but just this pattern where it starts at 0 and then, 0 at the top here and then hits 0 at pi over 2. What function does that remind you of? Guess what? It's cosine. So we didn't necessarily prove this. We just went through sort of that idea of trying to estimate the graph of the derivative, but it is in fact going to be cosine. So our derivative of sine is cosine. So I want you to pause the video and try the same thing for cosine, where you're going to try to sketch the graph using the same logic that we just did, and then see if you recognize that graph to identify what the derivative of cosine is. All right, so I've drawn in my picture. I did the same process, started with the places that had horizontal tangent lines. Those were my zeros. And then just looked at decreasing, increasing, and that pattern repeats. So what function does this look like? It's not quite sine, because sine does start here, but it starts up and then goes down. Aha, it's negative sine. It's the reflection of sine. So now we have two of our trig derivatives. We know the derivative of sine is cosine, and the derivative of cosine is negative sine. And so we're going to just take a few problems where we're going to use that knowledge of those two derivatives and build them into product rules and quotient rules and that kind of thing. So we'll start with our first problem here. Find the derivative of each and be sure to simplify. So I have y equals x times sine x. So this is a product. We're going to need to use the product rule. So y prime will be x times the derivative of sine x, which we now know to be cosine x, plus sine x times the derivative of x, which is just 1. So not a lot of actual simplifying going on there. Just kind of a straight application of the product rule. So we'll try the next one. The next one has sine of x over 1 plus cosine x. So we're going to need to use the quotient rule here. So y prime is low d high, the derivative of sine is cosine, minus high d low, the derivative of 1 is 0, and the derivative of cosine is negative sine. All over low, low. And so now we are going to have to do some simplifying. Let's see, it looks like I'll distribute my cosine and multiply out these two things here. So I have cosine x plus cosine squared x plus sine squared x over 1 plus cosine x quantity squared. And hopefully you notice a little something here. What is cosine squared x plus sine squared x? It's a 1. So cosine x plus 1 over 1 plus cosine x quantity squared. And that can cancel with one of those. So I'll be left with just 1 over 1 plus cosine of x. Okay. So just be aware you are going to need to know the basic trigonometric identities. The Pythagoreans, like sine squared plus cosine squared equals 1, 1 plus tangent squared equals secant squared. You'll need to know those because you can't simplify all these things without those basic trig identities. You do not need to know like cosine of a plus b and that kind of thing, but definitely the Pythagorean ones and the reciprocal ones, which we're going to use on both 3 and 4 here. So we don't know yet what the derivative of tangent x is, but we can figure it out if we rewrite tangent as sine x over cosine x. So that's another one of those basic identities we should know. And we're going to do number 4 by rewriting cosecant x as 1 over sine x. So that's one of those reciprocal identities that I'm referring to. You should know which ones of these functions are reciprocals of the other. Okay, so both 3 and 4, we're going to apply a quotient rule. And we're going to then try to simplify and see if we can't come up with formulas for the derivative of tangent and the derivative of cosecant. So again, I'd encourage you to go ahead and hit pause on the video and see if you can work out the quotient rules in those two situations and then restart. Okay, so let's go ahead and just walk through these real fast. I am applying my low d high minus high d low to sine x over cosine x all over low low. I end up once again with cosine squared plus sine squared, which is a 1. And 1 over cosine squared will give me secant squared. So our derivative of tangent is secant squared. Same idea number 4, but when I do low d high, the derivative of the top is just 0. So that's going to go away. Minus high d low. So I have just a negative cosine x on top. But you'll notice I rewrote the sine squared as sine times sine, because then that allows you to think of negative cosine over sine as negative cotangent times 1 over sine as cosecant. And so we traditionally use negative cosecant x cotangent x as the derivative of cosecant. All right, I got a couple more here. So just, using our motion that we have talked about, position, velocity, acceleration, we have a problem that then uses trigonometry in those functions. So we have a particle moving along a coordinate axis in such a way that its position, so here's our s of t function, is given by this. At what time is the particle at rest? So I don't know that we've answered one of these in the notes yet. Particle at rest. So what's going to tell you when the particle is at rest? It's not the position, it's the velocity. And what is the velocity going to be when a particle is at rest? 0. So what we are talking about in this particular problem is to find the velocity function first. I guess I could write it this way, just to be a little bit more clear. This is asking us, when is v equal to 0? So we're going to need to find the velocity function first and then set it equal to 0. So velocity will be the derivative of position. So when I take the derivative of 2 sine t, I'll get 2 cosine t minus the derivative of t, which is 1. And then I'm going to set that equal to 0. So I'm looking at, when is cosine t equal to 1/2? And we're going to have 2 answers in this interval from 0 to 2t, because cosine is positive in 2 different quadrants. You may or may not remember all of your trigonometry details. All students take calculus was one way to remember what's positive in what quadrant. All of them are positive in the first quadrant. Sine is positive in the second quadrant, so is its reciprocal cosecant. Tangent is positive in the third quadrant and is reciprocal cotangent. And then cosine and secant are positive in the fourth quadrant. So I'm going to be looking for a first and fourth quadrant angle. And if my cosine is 1/2, I know some of you have memorized the unit circle, but I can't. It's just ridiculous, in my opinion. So instead, I just use my triangles. I realize that my triangle is a little bit, let me see if I can't draw it with a thinner line. So this would be my pi over 6, which is 30 degrees. This would be my pi over 3, which is 60 degrees. And so now I'm just looking for, when is my cosine 1/2? 1 over 2, and cosine means that the 1 is adjacent. So that would be a pi over 3. That will be pi over 3 in quadrant 1. And if this is pi over 3 in quadrant 4, going all the way around will give me 5 pi over 3, or 1 pi over 3 less than a full rotation, which is 2 pi. So those are going to be my 2 answers for when the velocity is equal to 0. And then my second part of this question is asking me to find velocity at 4 pi over 3. And so I'll need to plug that in. I actually already know 4 pi over 3 is going to be in this third quadrant with that same reference angle. So it won't be 1/2, it'll be -1/2, the cosine. So 2 times -1/2 minus 1. So I've got -2 for my velocity at the time 4π/3. And then I need to do the acceleration at that same time. So I haven't found the acceleration function yet. I should probably do that first. I'm going to take the derivative of my velocity. So the derivative of 2 cosine, which will be negative sine. And then the derivative of 0, I'm sorry, of 1 is just 0. So this is -2 sine of t. So if I plug in 4π/3, get -2, and now I need the sine of 4π/3. I'm going to use the same triangle. Pi/3 has a sine of √3/2. If I'm in the third quadrant at 4π/3, then that sign will be negative. So this will be -√3/2. And so my answer will be positive square root of 3. Okay, and then it's asking me to do one more thing. Compare these values and determine whether the object is speeding up or slowing down. So a lot of people feel like they only need to look at acceleration to determine whether something is speeding up or slowing down. If acceleration is positive, then it must be speeding up. But that's not necessarily the case because velocity itself can also be positive or negative. So here, let's take this specific example to try to illustrate this idea. So we have a positive acceleration. And what that means is that velocity is increasing, right? It's the derivative, it's positive. So that means the function that it's the derivative of must be increasing, getting bigger. But velocity, oops, is negative. It's a negative number. So if a negative is increasing, an increasing negative is going which way? Is it getting more negative or less negative? It's getting less negative. If it's increasing, it's getting a higher value, which means it's getting, for a negative number, it's getting closer to 0. So an increasing negative is becoming less negative. So if its speed started at -2, it's increasing, it's becoming something like -1. That's just an example. So talk to me about speed. Is the speed of that object from here to here faster or slower? It's slower because speed is the absolute value of velocity. So it was going 2 in the negative direction, and now 2 feet per second or whatever it might be, and now it's going only 1 foot per second in the negative direction. So this object is actually slowing down. And that is because when the acceleration is positive, but the velocity is negative, it's getting less negative. So its absolute value is getting smaller.